0, then we'll get back to the idle state. Okay. Okay. Have you copied this simple till this diagram? Okay, I'm going to continue on this diagram. Did you copy this diagram?
Yes.
Okay, so let's start coding. Okay, so the diagram. Okay. Share notepad plus. Okay, let's say we have module RTL example 1. Okay, till now we have input clock reset, and till now we have, let's say, input start I. Okay, right now. Okay, so local param. Okay, as I told you, idle equals to 0. We are having till now we have the state register. Okay, let's make something like this: state reg, state next. Okay, the sequential part, edge of clock, I'm going to have with the synchronous reset. Reset equals to 1v1. Zero and next. Okay, and the combinational. So I'm going to write here sequential logic. Okay, and then combinational logic. Okay, so always I usually will put star, which means every signal within the design. I use this star because in many cases I may have something like 20-30 inputs to that combinational block, and that's why I prefer to use this in order not to forget, because it's easy to forget one signal, and especially in the simulation it may get crappy. Okay, usually for by the way, what does it mean, this initialization of the state? So I put here state next equals to state reg. Why do you think that I put this? What this translates? So if I'm having this code, okay, here, okay, what does it mean? This block, what actually means?
That the next state will always be the same as the current state.
Okay, so actually it will mean that it will keep the state. So by default, the state register will keep its state. Okay, so this is what it means. Okay, this is by default. Okay, okay, and as I told you, most of the things are based on the states. So in the idle state, till now, to what we have in that diagram is start of I equals to 0. Okay, state next it remains in the idle. Okay, so this is and I'm gonna put also the AND case. Okay, okay. Okay, let them file, and this is the example. Okay, so this is what I have brought till now. Okay, so I'm going to switch back to the drawing. So let's say we have a very simple example in the sense that I'm going to add to make the sum of all the numbers from 1 till n. Okay, so if I want to make the sum of all the numbers from 1 to till n, let's say we have like this. This is the start. This start actually it's an input control signal. Okay, so basically this will lead into a state where the things that need to happen will happen. Okay, and first of all, I'm going to take an input, an outside input. Okay. Okay, so how should I call the input? Let's say n is equals to input n. Okay, and of course, because I want to make the sum for from 0 till n, so this is the algorithm, then I need to have a variable which stores the sum. Okay, so this is the input phase. Okay, state. Okay, so this and okay, so the code will lead sure. Okay, so I have RAM input is equals to 1, and then I have an input here, say a data input. Let's say it's okay on 8 bits, of course, and of course I will have an output. Okay, sum out. Okay, sum home. Okay. So I had here I have two variables. Okay, so you see here two variables, it's n and it's s. Okay, good. So basically for these two variables, I'm going to declare two registers. Okay. I'm going to make I will have the signals and reg and next. With n reg, it's the output for the n variable. S next, s reg, it's the output for the s variable, and so on. Okay, so I'm going to have another decision here. Okay, and this would you like a counter also?
Yes.
Okay. Okay, so I'm going to have also a counter here. So the classic counter I equals to 0. Okay. And the condition is, let's have here, if I equals to n. Okay, so this is for the input phase. Okay, and did you copy? Okay, so I'm going to stop and I'm going to write. Go. So as I told you, we have there three variables. Let's say sigma 0 and reg and next reg as reg as next reg I reg I next. Okay. So I have the input phase. Okay. Here as begin state next, it's the input phase. So in the idle state, what I'm doing is checking the start. If it's 1, then I'm going to go into the input phase. Okay, and in the input phase, I'm going to have, and next it's ni. Okay, and this corresponds, and next it's ni. As next it's 0, and I next it's 0. Okay. Okay, and now I will explain a little bit later. The condition I will put here, it's on the next variables, and I would explain. Okay, if it equals begin and okay. Else and okay, so this is for the second state. Okay, and this also will have to include this register in the sequential logic. Reg equals 0, s reg equals to 0, I reg equals to 0, the same. And next, s next, I next. Okay, and the same initialization, and next equals to n reg. Okay, s next equals to s reg, I next equals to I reg. Okay, good. So this is for the input phase. Okay. Okay, and I have this decision here. So
I have a question.
yes,
Does the circle represent the same thing as the rectangle in this diagram?
yes, they represent the same thing, except that usually in circles you don't do anything. You know what I'm saying?
Okay.
So the rectangle, usually I have a data operation, as you can see in that rectangle. Okay, in the circle I don't have anything. Okay, so I'm going to go a little bit when I'm finishing the example. Okay, so I'm going to get here, and I'm going to have a little bit of more states. So let's say, first of all, I can do that in the same state, but let me do it. I will do on purpose in two separate states. So first of all, I'm going to make I equals to I plus, sorry, S equals to S plus I. Okay, and then I'm going to have, okay, let's say I equals to +1. Okay, okay, and from this I equals to way. Okay, good. So let's call this two states here sum compute. Okay, this is the sum, and this is the increment state. Okay, so these are okay. I'm going to switch. Let me finish also the diagram. Okay, I'm going to have another state here. Okay, In this state, let's say sum O equals to S, and I have ready output equals to 1. Okay. This is the here out state. Okay. And from this out state, I'm going to the initial. I'm going to back to the initial state. Okay. So okay. One here on this branch if it's 0. Okay, so this is actually the algorithmic diagram, as you probably know. As you can see, here you have these variables, and from the code, you saw that for the variables, I have registers. I have a data output. Okay, this is the sum O. I have a status output. It is the ready O, which is 1 only when we are in the last stage and last state, and we want to we put the output, the sum on the output of the circuit. Okay, and here we have states where we perform multiple operations. It's not the optimal way of, okay, because did you copy this diagram?
Yes.
Okay, so okay, so if we, in the input I have, let's say, sum equals to 2 local param. Okay, out as okay, and I also will have another output ready O. Okay, now for the outputs, okay, I also will initialize here because they are data output. Somehow it's the data output initialization, it's usually with 0 for the data output. For the ready, is default state, it's also 0. And basically, for example, in the idle state, okay, what are the values in the idle state for the sum and for the ready?
But they both should be 0.
They should be 0. They are the value. These actually are the default values. Yeah. Okay. So here in the input phase, I have this n next equals to I next. If they are equal, then stay next is the out s. Okay. Otherwise, stay next is sum. Okay. Let's go with the sum. in. In this case, I'm having s next equals to s reg plus I reg, okay, and state next equals to inc, and in the increment, usually, not usually, I'm having I next, it's I reg plus 1, that's the counter, okay, and I have the condition if I next equals to I, and I'm going to explain why I choose like this. State next, it's next it's sum, and okay, and I have the last state out s ready equals to 1, state next, and I have the RTL code for the algorithmic diagram that I had that I draw earlier. Okay, so I had a very trivial, a trivial algorithm, very simple kind of algorithm. As you can see, one thing that it's really helpful is to have this algorithm in a more or less state diagram, okay, an algorithmic diagram where you have the states and you have the operations within each state. For example, you have in 5 out of 6 in 4 out of 5 states, okay, you have data operation, you have a data operation, you have actually 3 data operation in the input phase, okay. It's the update of the data register N, S, and I. You have an data operation also in the sum state on variable S, so it's you update the register corresponding to the variable S. You have also data operation in the increment state, okay, and also in the out S, okay. So this is for the diagram, okay. Now for the code, okay. So this is regarding the code. The thing here, the main okay, except these branches here, the input, the if condition here and the if condition here. Is there any other question related to the finished state, to the implementation of this finished state machine with the data path?
For instance, regarding the ready output,
Yes.
is it okay to leave out the initialization for ready output since it is by default 0?
As you can see, the ready output it's by default 0 here. Given this, okay, in this line, okay, you see this line.
Yes.
At 56, okay. If you don't put this line, okay, and I'm not talking about 0, okay. Radio, it's not a register, okay. So for example, at reset, you don't put radio on a predefined value, okay. Of course, that predefined value, it's most of the time, how should I say, most of the time it's 0, yeah. But you don't put this radio on a predefined value, okay. And as you can see in this radio, it's actually an combinational output. It's not a sequential output, okay. And this combinational output has to be defined for all the branches in this case, okay. That's why I should have put that radio basically in every branch, in the branches of the case and also the branches of the if, okay. And with this initialization, basically I'm predefining to a value, okay. 0 is the value that suits me, and that's why I don't have to write it already equals to 0 in every state, for example. Did you get it?
Yes, okay. So we have, I mean, it's ideal to choose a default value that suits the problem.
Exactly. Usually for combination, that's usually, okay. So there are exceptions. For combinational signals, you put 0, okay. For sequential, for registers, you put to preserve its value. So it's the next equals to rec. That's the most, that are the most, the typical way of initialization, you know. So in order, as you can see, you don't have, because if you don't put it, you need to put in every branch here, you need to put the values, okay. So I'm not putting there in every branch, which makes actually the code more tractable, okay, because to have these 6 lines of code, and in other cases this 6 line may go into 20, okay, in every case it will be a big headache, you know what I'm saying.
Okay, but in general, can't we choose to have the sum O be the same as the register of sum instead of putting it to 0 in all situations instead of...
You can have like this, okay, for example. Okay, so to be default value to be as rec, okay. And yeah, that's a possibility. I'm not, in this case, I'm not going to the, let's say the, to the optimality of these things, okay. So that's not optimal. Anyhow, the algorithm, it's this thing, it's very simple, okay, it's trivial, okay. So I'm not going into this case, it's just to present how to go from to write the code based on algorithmic description, you know what I'm saying. Okay, so about this condition, okay. First of all, you see this condition performed on the n and I variable, okay, are performed in the same state where there are the updates. So basically in the input phase, you perform an update on the n next. Also in the input phase, you perform an update on the I next, correct? So if you want to make the interrogation on the last value for the variable, on the value actually you will update, okay, because for example here n next n reg, actually it's it will remain with the undefined value, okay. You perform the algorithm once, okay, you have an n reg. I didn't put any kind of initialization or so on, n variable in this algorithm. Okay, so basically you have on the n the value that you want to take into account is this and I, okay, which you update in the same clock cycle in the same state where you put also the interrogation. Okay, so you put the interrogation here and you want to put actually on this NI, and that's why you have here and next. Okay, now for example in this case, okay, you perform an update on I, okay, and you want to make the interrogation on the last value, which is the updated value of the variable I, and that's why you have here I next. However, regarding the n, that's you don't have the update on the n register. Okay, you will put actually on its reg value because you don't have actually here update. Usually you put next only when you have the update in the same clock cycle, which means actually in the same state as the variable in the interrogation. Okay, so basically here you have the update on I, you don't have the update on n, and that's why you put the I next in the if, and you have the n reg in the if. Okay, questions if you have.
I have a question.
Yes.
Do you think you can maybe upload what we are doing?
Okay, I will put. Okay,
on
I
the
will.
campus virtual.
Okay, I will put an upload. Okay.
Thank you.
Okay, so this is first example. Okay, so let's go. I would like you to have the diagram. You can write it by hand and make a photo or a scan of it for the multiplication by repeated additions. And then we will start to write the code. Can you do it now? Till then, I'm going to have another simple example in the background. So please do the algorithmic diagram. I will. You have the possibility to share, and also if you want to write, then you'll start writing the code. When you finish the algorithmic diagram, just say okay. You can announce me about this, okay? Did anyone finished?
Recording in progress. Recording stopped.
Okay, so I had internet problem and I was disconnected. Okay, did anyone finish the diagram for the repeated addition based multiplication? Has anybody finished?
I think I did.
Okay, so 1 minute and you'll make a share screen. Okay. Okay, so you can have a share screen.
Okay, one moment.
Okay. So okay, if it's by the way, okay, m equals to 0, then okay, good. So the state diagram looks like this, okay, which is perfectly okay, in the sense that you add to the m a b times, okay. So that's a very simple diagram, okay. The others, please try to copy. You can try to have the code for it, okay. So you can start writing the code. In any editor you want. Did you copy the diagram?
Yes.
Okay, so you can stop your share,
Okay.
Stefan. So you can write the RTL code. By the way, has anyone finished the first assignment for the lab?
I did.
I have a question. Are we supposed to have it done by tomorrow?
You can have it whenever you want. Tomorrow I'll present the second assignment, okay? And of course, my presentation for the assignments and the way I let's say envision the how these assignments should be okay, uploaded and so on, presented, okay, are taking into consideration that you want a tab for the lab, okay? That's why you can present till the end of the semester anytime, okay, any week actually, but okay, and as I told you, the grade, it's incremental. Okay, who wants to share a screen with the code snippet from what you do till now? What you did till now? Does anyone wants to present a code snippet? Stefan, can you present it till now? What you have written? Oh, okay. Okay, so you can stop your share. Has any other one from you has started to write the code?
Yes, I did.
Okay. When you start to writing states and so on, can you share?
Okay.
Okay. I don't want all of my courses to be just story presenting, okay? So I'm just to present from the slide. I would also like for you to try different stuff, okay? At least you will have a skill. Paula, can you share?
Yes. Can you see?
Okay. So the multiplication, okay, you have some n in. Why it's the same input? Okay, you should have a and b. For example, yeah.
I have N in and in.
N and M, okay. So you have these N and M registers, okay. You should have, okay, and because you have you want to N by M, am I right? N multiplied by,
15 here.
okay, it doesn't matter that the size so much, okay. So you want an N by M multiplication. So you want the register N and you want the register M, okay. You don't have any I, correct?
Actually, I'm using I as a counter, and I count until M, and
Okay,
I,
you can use also, you can also decrease the one of the two inputs, okay.
yes.
Okay, so the sum, okay, and that's the state reg, okay, and I wait to write the code for the input phase.
Can I share when I'm done? Because I'm not sure.
Yes, okay, you can share when you're done. Anyone finished? Okay, who wants to make a screen share?
I can share.
Okay,
I'm doing this
okay, so
one state and I'm
So-
using I.
so you are actually you are making okay, you have also the counter, okay, and x equals to min, okay. The only thing, okay, is that in the product compute state, okay, in the product compute, you don't go into a new state. You will remain there. No, the next
I'm
line.
going to out state.
Okay, and by the way, what will be the condition in the product compute?
If I reached M in, then I should go to out state.
Okay, the thing is that you should load the M input into a register, okay, because you don't know in the product compute state, which may pass multiple times, okay, if it will be the same as the one that you wanted to load into the input, okay. So you load the input into a register, basically you save the input into the register, okay.
Yes.
It's the same as you save inputs into variables as in programming, okay, either from the they read from a file. Okay, you don't open, for example, many times, only when you have large amounts of data, you open the files and so on. Okay. Did you understood?
Yes.
Okay. Who also wrote the code? Stefan? Can you have a share screen?
Oh, well, I'm still at the input state.
Okay. Any other one? Okay, so try to have it till tomorrow. I will open up a form of an assignment, okay, and you can upload there. And if you have questions, we can discuss it tomorrow. Tomorrow I'm going to present how to make instances into the RTL description. This is actually the basic for presentation for the RTL, which you have starting from a diagram, an algorithm description, you implement this code. And no matter how big the complicated the RTL, these are the steps. Actually, more complicated, it's the algorithmic description. So I'll make an assignment for until tomorrow, and we'll meet tomorrow morning at 8:20. If you have questions, if you don't, thank you.